All right, it's 11:15. We'll get started. So don't forget your PLA. I gave you an extra day on it just so I remembered, you'd remember, but it's due tonight for today. So it's the day of lecture assignment this time. You have a couple of PLAs this week. You have a homework due this week before spring break on Friday. So make sure you turn that in. We are having class on Friday. And so you're welcome to leave whenever you want after class, but we will be taking attendance and all the usual stuff. And then when you come back after spring break, of course, no in-person classes next week, no videos next week, no homework, no nothing. You will have PLAs when you come back, but I assign that one to be due on Monday as well. So you don't have a PLA on Sunday of spring break because that's just not cool. So anyway, the PLAs are a little bit offset. They won't be like that for the rest of the semester, but with exams and breaks and whatever, you know, I wanted to give you a little leeway. So make sure that you get the PLAs done, make sure you get the homework done, and I will have office hours this week if you have questions on your exam. I think everyone took it successfully. I didn't hear about any major issues, and I'll be grading your written part over the next couple of days. Also, I updated the iClickers. Some of you have excused absences that I tried to include. You know, if you forget your clicker, it's hard for me to help you. But if you have excused absences, just remind me. When I update the iClicker, it doesn't take into account excused absences, so I need to put those in by hand. And remember, for clicker participation, you just have to be above 75% to get full credit. And there's going to be, you know, roughly 25 or 27 participation points. So missing 1 or 2 or 3 isn't a big deal. But if you start to miss too many participations in your iClicker, you'll get less than full credit. So just pay attention to that. But, you know, 1 or 2 points isn't going to kill you. And if you're on the borderline, at the end of the semester in terms of grades or your percentage, we can communicate about that. But otherwise, we're starting section 3. The notes are up, the homework's posted, sort of a regular week this week, and then we get a well-deserved week off, I think. Any questions or comments? Okay, make sure to finish this week strong, and then we'll go on spring break or stay on spring break, whatever you're doing. All right, so we're going to take on a couple of things in this section. If you look, if you look on the syllabus, there's actually not that many topics in this exam 3 period. And we're going to have 2 homeworks and we're going to take an exam just like we've done in the past. So you can see when that 3rd exam is going to be. Make sure you're prepared for that when you come back. But, you know, exam 2 was pretty packed. Exam 1 was all brand new stuff. Exam 3 gives you a little bit of space to collect yourself in the middle of the semester here. So we're going to talk about ring opening polymerization. And ring opening polymerization is a type of chain growth polymerization. So you want to make sure that this falls under chain. Oh, if I can draw. Chain growth. And it proceeds by anionic, cationic, or radical. There aren't lots of examples of radical chain growth polymerization, but we're going to look at the mechanisms of anionic and cationic. So you know exactly what class of polymerizations it falls under. And it's called ring opening polymerization because this is a cyclic monomer. And that may seem weird in organic chemistry. It's weird to see a lot of cyclic molecules except for benzene and aromatic groups. But it turns out some really important polymers are made this way. And so that's why we study ring opening polymerization. That's why it's an important class of polymers to think about. And so it's a chain growth, which means that you don't gain or lose any atoms or functional groups. Don't gain or lose atoms or functional groups. Which means the chemistry that you see in the ring is exactly the chemistry that you see in the polymer repeat unit. So if you look at this RZ, this is same as in monomer ring. And that's a hint. That's a really easy way to think about, okay, what is my polymer repeat unit? What is the monomer ring going to look like? Or what does my monomer ring look like? And then I can go right to the repeat unit. And we'll have some examples of this. But this is a big hint for sorting out what's happening with ring opening polymerization. And so this is how you'll see some rings represented. You'll have to be okay with this type of nomenclature. But this is basically 5 carbons in this CH2 here, plus this carbonyl here, plus this nitrogen here. So this is a 7-membered ring. Sorry, let me not draw that stylized 7-membered ring. Just count the number of atoms in the ring, and that's what's in there. So in this unit, we're gonna ring open 3-membered rings, 4-membered rings, 5-member, 6-member, 7-member. There's actually an 8-member ring opening polymerization that we won't study, but it might crop up if we have cyclooctene. But those are the common types of monomers that we talk about. So it can go from 3 atoms in the ring all the way up to about 8. There aren't a lot of other types of ring opening polymerizations. And so when we draw something that looks funny like this, we can write it out just like this. So nothing funny going on with that carbon chain. We just draw them connected all together, and we draw a curve because we have to close the ring. What type of molecule is this? What is that functional group really looking like to you? Carbonyl connected to nitrogen. Amide, right? It's called something else when it's a ring. It's called a lactam, but this is a amide. And so based on what I told you on this slide, if I open a ring that contains an amide, what type of polymer do you think I'm going to get? Polyamide. It's that simple, right? So this thing makes a polyamide. Or a nylon, right? Because you know polyamides and nylons are the same thing. And so nylon 6, which is the predominant form of nylon in Europe, is made using ring opening polymerization. Nylon 6,6, which is the predominant form of nylon material in the United States, is made using condensation polymerization of 2 different monomers. And that is for patent reasons back when the chemical industry was invented. So, any questions on this slide? Any comments? All right, remember that the ring chemistry translates to the polymer chemistry. So you should be able to figure out how to turn that 7-member amide into a polyamide. And so we have some ethers. So we call this ethylene oxide. That's just its common name. But this is an ether because it's oxygen bonded to 2 aliphatic carbons. And so PEO, or polyethylene oxide, is a common polymer made from this ring opening of ethylene oxide. And you can see I've got my oxygen here. I've got 1 carbon here. And I've got another carbon in another color, assuming I can get that color. I've got 1 carbon here. And so this is pretty easy because there's only 3 atoms in the repeat unit. Let me get back to my red. And so you notice, since both of those carbons are connected to the oxygen, when I stretch it out, when I open it up, both of those carbons are connected to the oxygen. One is one way, one is the other way. And you know, I can slide those arrows wherever I want. So I could draw PEO like this. That's the exact same polymer that's shown there. Yes, question.
Yeah, I was gonna ask if it matters, like if it's going up and down or if it starts like down to up.
The only thing that matters is I have the right number of carbons, the right number of hydrogens, and the right number of oxygens. So depending on how you like to draw chemical structures, you remember from the first unit that as long as you can understand where everything is happening, as long as I can understand it, we can interpret it. So whether you use a stick figure, whether you write in all the atoms, et cetera, where you put the parentheses, it doesn't matter. So all of those same rules hold for this. Doesn't matter if it's up, doesn't matter if it's down. You know that a kink in a line usually means a CH2, right? Unless something funny is going on. And so there's lots of different ways that you can think about writing these repeat units. And so this is worth practicing. All right, polypropylene oxide. So ethylene oxide has 2 carbons, polypropylene oxide has 3. And so we look at that methyl group, and the methyl group is right next or attached to the carbon attached to the oxygen. Again, they both are. So we just need one carbon with a methyl group and 1 carbon without one. Now, depending on how we handle this, so this is caprolactam. I told you it's an amide, but it's called a lactam when it's a ring. That's an old nomenclature. And capro is a really old nomenclature, which means 7. And so caprolactam turns into polycaprolactam, or this is a polyamide. And so this is the monomer that forms nylon 6 because we've got 1, 2, 3, 4, 5, 6 carbons, even though there's 7 members in that ring. We don't count the nitrogen. And if you look at nylon 6,6, it's got a different chemical structure than nylon 6, which is really interesting. So if you write out the structure for nylon 6,6, which is a condensation of RA2, RB2 monomers, and nylon 6,6 and nylon 6, you'll notice that they're different. But we have this polyamide because this functional group is right in the ring. And so we can write that monomer a number of different ways. So don't forget, again, about sliding those parentheses, whether we break up this amide and put 1 carbonyl on the other side, or we put some carbons in between, you know, a few of these carbons on one side versus the other side. It doesn't matter as long as we keep the connectivity, right? This is a polyamide, so you need to make sure the carbonyl and the nitrogen are next to one another, and you have the appropriate amount of carbons in the rest of the structure, but you can write this however you see it and however you feel comfortable doing that. Questions or comments on that? All right. And there are just a few classes of polymers. The one example on this that's missing is a polyester. So I'll just say polyesters can be made using ring opening polymerization. We'll see examples of that. Polyolefins, it turns out, can be made using ring opening polymerization as well, but I'll give you some examples. So we can't make every single polymer this way, just some really important ones. All right, so why do we use a cyclic monomer? In some cases, those cyclic monomers are available. They're actually a thermodynamically favorable product from the petrochemical industry. But in other ways, because of the ring strain, we get very favorable thermodynamics in terms of using that ring strain to make a polymer in the first place. So you know that a low number of carbons give you high ring strain. Those are very reactive monomers. So ethylene oxide is explosive. You have to handle it very carefully. And as the ring gets bigger, the ring strain goes down. They're not as energetically favorable. And so there's some interesting reasons why we use cyclic monomers, but ring strain is a really important one. So higher strained rings. or smaller more highly strained rings are more reactive. And if you have a more reactive monomer, it's easier to make a polymer out of it, or it's more favorable to make a polymer. All right, so cationic ring opening of epoxide. So epoxide is the generic name for this functional group. So even this thing is called ethylene oxide. This is an epoxide. And we can be formal and put an R there. Yes.
I just had a question about the last slide.
Yep.
So in the PLA, it says that larger rings have less strain and have more steric repulsion, so are more unstable. Is that true?
It depends on exactly how big it is or what the conformation is. And so, you know, there's subtle effects in terms of entropy and other things going on when we do ring opening of bigger rings. And so the main one is this, that ring strain is important, but there are subtle effects in larger rings. You should just file that in your memory bank. We won't talk about the energetics a lot, but we should talk about this because ethylene oxide is an explosive chemical. Yeah. Yeah, if we get into really subtle energetics of ring opening, I will talk about that in detail. Yeah. Okay, so let me write this so the R is not over my sheet. So the epoxide functional group, just like your other functional groups, is this 3-membered ring and one of the members is oxygen. So if we're going to do cationic initiation, the cation is the initiator, right? And the active center is cation, because we name the polymerization from the type of active center, right? And so we need to think about how do you get a cation in terms of this 3-membered rings. And we don't put the cation on oxygen. Why? You know, we take the 2 electrons from oxygen because there's a lone pair right there. That's fine. We can make a covalent bond. But why don't we put the positive charge on oxygen versus carbon? Yes. It's more electronegative than carbon. That's right. Yeah, yeah. So oxygen is more electronegative than carbon. And so it wants its full complement of electrons. It grabs another lone pair from this covalent bond right there, satisfy the octet of oxygen. That's fine. And then it turns out that carbon can support plus charge. Oxygen cannot. So when we're doing cationic polymerization or cationic ring opening polymerization, don't put the positive charge on oxygen. And so that covalent bond, I'm going to erase my little dot right here. Notice where you form the attack. So the initial attack is from oxygen, which has lone pair, and then you bring over 2 more electrons from the covalent bond. So that's worth studying, because then it gets easy for propagation. It's exactly the same thing. So in our propagation step, you take 2 lone pairs. Let me see, I don't really have a good pointer. You take 2 lone pairs, or you take a lone pair from oxygen. You make the covalent bond to the active center because you need 2 electrons, since that's a cation. You need 2 electrons to make a covalent bond. The 2 electrons from the covalent bond in the epoxide go back to oxygen, and then you open up the ring to get a cationic carbon, and you have your balancing anion. And because cationic polymerization terminates via ion pair rearrangement, you get exactly the same thing in cationic ring opening. So this step right here is exactly the same as we studied for regular cationic polymerization. Yes.
So since it's in equilibrium, will chandeliers will at all like affect like if there's more product there would be more of this kind of formation, or if there's not enough to meet this conformation?
Conformation. So Le Chatelier is based on moles, right, or molecules. It's not really based on conformations too much. And we haven't talked about conformations here. Le Chatelier is indicated by these reversible arrows, right? So go ahead and ask your question again about conformation. Yeah, so you actually promote polymerization by adding more monomers. So Le Chatelier works for everything. And so these polymerizations slow down when you run out of monomer. And so if you put more monomer in, you push the equilibrium towards polymer. That's actually a technique that we're going to talk about in like a lecture or a lecture and a half. We're going to talk about how that's done in terms of running out of one reactant versus the other. But all these reactions are reversible. And so you can always get some reverse reaction, right? And so people who make polymers use Le Chatelier's principle to sort of adjust that equilibrium, but not in terms of conformation. All right, you get cationic ring opening polymerization chain transfer, and the only thing you need to know about this is that you can get rings from this process. So this is, what type of chain transfer is this? If we look at this diagram, intramolecular chain transfer. And what you do is you actually make rings and chains from this process. That's just really interesting. So you can get small rings split off in intramolecular chain transfer from cationic polymerization. Okay. Clicker question. Remember, we are on AC. CD. I don't know why I said AC. This thing says AC. I have no earthly clue why. Maybe we had AC one year. CD, please. All right. Polymer below is formed from ring opening polymerization of the below monomer. So this is our monomer. I gave you the polymer structure. And so notice we've got our CH2s. Those are not chiral centers, but now we've got chiral centers here, 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 here. So we have to look at each of those chiral centers and evaluate what the stereochemistry is down that chain. So I know we have more than 34 people here, so you can continue to ring in. So the stereochemical configuration needs to be adjusted, right? So you need to take these functional groups and rotate them all the other direction, so we can see them all on one side of the chain in the stereochemical projection, and then you can evaluate what this tacticity is. All right, are we gonna get to 50 today? Maybe not. And so if you rotate those functional groups, R is coming out at you or out of the board in each of these cases. And so this is an isotactic polymer. And this is a little bit hard to count because you notice, well, what's this polymer going to look like? Do I have the right number of substituents? But anytime you have a substituent on this epoxide, this can lead to tacticity. Or it can be atactic. So if you count carefully, there's 4 different functional groups on the carbon right here. 4 different . So don't forget about all the hydrogens on that monomer, right? Because doesn't quite look the same as we've done before. Okay, great. Let me stop my clicker. Anionic ring opening of epoxides, and now in the same vein as cationic, the anionic charge sits on oxygen because oxygen is more electronegative than carbon, and so it holds on to that negative charge. And so the active chain end is different in anionic versus cationic ring opening polymerization, but you get exactly the same monomer or exactly the same polymer. So if you have an epoxide-based monomer and you do cationic ring opening versus anionic ring opening, you have different active centers, but they lead exactly to the same polymer. And so since this is an anionic initiation, the anion initiates, it actually attacks the carbon. So it looks a little bit different, right, than cationic initiation. But you get attack at the carbon, the lone pair goes up to oxygen where your excess negative charges. Now you have an anionic active center. On oxygen, and it attacks the carbon of the next monomer, et cetera, et cetera, et cetera. Why doesn't this oxygen anion attack the oxygen? I mean, in cationic polymerization, you know, we took our cation, right? So here's the cationic active center, and it attacked the oxygen, and that's the way you open the ring. Why don't we do the same process? Here. Whoop. Where am I? Here. First off, we would make an oxygen-oxygen bond, and that's not something we want to do because that's a peroxide. And so that's not the type of polymer we're making. And there's already a bunch of electrons, including lone pairs, around oxygen, right? There's lots of negative charge around that, but because oxygen is more electronegative than carbon, remember you have a little delta minus and you have a little delta plus. So if you look at the partial charges, that excess negative charge in the active center wants to attack a partial positive charge. That's easiest route of attack. Why doesn't it attack the other carbon? Why did I draw it this way? Sterics, right? That R group is in the way. So doesn't attack R group carbon due to sterics. Okay, so this has helped to get our feet wet in cationic ring opening polymerization, anionic ring opening polymerization. Yes. Because we have N here, and we've added one monomer here, and so that gives you N plus one monomers in that chain now. Yeah. That's just the way they do it, right? It could be N. Well, it could be any letter. You're just adding one monomer. Okay. So that gets your feet wet in cationic and anionic ring opening polymerization of epoxides. And you should write down these mechanisms for a few different monomers and make sure you get the active centers in the right places. And so other types of monomers that are really important are lactones, lactams, and cyclic ethers. Cyclic ethers, which are like epoxides, but with more CH2 groups. and we'll go through that. So the lactones and lactams, that's just an old nomenclature. It's okay if you call them cyclic esters and cyclic amides. I'll try not to use too much ancient nomenclature with you, but once you go out into the real world and you start hearing about lactones and lactams, now you know what they are. And they make polylactams. No one really calls them polylactones. They're called polyesters, right? Because that's a common name. Only caprolactone or caprolactam and caprolactone are called polycaprolactam and polycaprolactone. But you'll learn that in your advanced polymer classes. Okay, so we have a couple examples of polymerization of lactone. What type of polymerization is this showing right here? How can we identify the type of polymerization based on what's going on? The active center, or we can look at what's the initiator. And so which mechanism is shown here? Anionic ring opening polymerization. So given this scheme, this is anionic, and of course we have propagation in the next step. Anionic ring opening polymerization. Great, and so we just look at the active center, and we've got that. And notice we ring open this cyclic ester, and we're making polyesters. That's check. Make sure we're good. If we're opening cyclic ethers, we're going to make polyether. If we're opening cyclic amides or lactams, we're going to get a polyamide. And so those are the big three classes of ring opening monomers you should know. All right, you can get out your clickers. Well, there's one other class of monomer I'll tell you about in a second. All right, we want to make a polyether. Which monomer is appropriate? And some of the questions should, be coming to you in terms of what's going on here. I think we were at 49 last time. Let's see if we can get all the way back to 49 or 50. Oh, maybe not. Okay, so polyether, we know that the chemistry is contained within the monomer, and so the right answer is B for that one. All right, the one chemistry that I didn't mention on this previous slide is this. Does anyone know what that molecule type is? It's a ring. It's real. It's not just a goofball molecule. Does anyone know what that is? Yes. It's close to a silicate. Siloxane. This is a siloxane. And so we can talk about silicon, the element, silicon, the element, silicone is polymer, silicate is a mineral. It's an inorganic mineral containing silicon and oxygen and some metals, aluminum, other stuff like that. Siloxanes or polysiloxanes are silicones. So this is the monomer for silicones, or polydimethyl siloxane, which is one of the common forms of silicone rubber. So like silicone bathroom caulk is polysiloxane based. And so in this ring opening monomer, you're going to have silicon, CH2, or CH3. Let's get all the hydrogens there represented. That's why it's called dimethyl siloxane. So if we ring open that monomer, and if you look very carefully, this is a repeating unit, and that's it. So they call this monomer D4, if you ever hear that. and you open it up to form polydimethyl siloxane or some sort of generic silicone. But you can see polymer, dimethyl, it's got 2 methyl groups on silicon, and you need 4 bonds to silicon, just like carbon, because silicon is 1 below on the periodic table. 2 bonds to oxygen, we're all set. So now this is one of the few polymers we've seen that doesn't contain carbon-carbon bonded backbone or have some flavor of carbon in the backbone, right? But this is worth thinking about because silicone rubbers are really important, and there's a lot of different silicones out there, but this now gets you familiar with some sort of synthetic rubbers or siloxanes or polysiloxanes. Great, but don't call them silicones, or don't call them silicon or silicates. Those are different things. Good. All right, we got that. All right, which monomer would you choose to make this polymer? So first off, what type of polymer is this? Polyester, right? And so this guy's out. But there's esters in all those 3 other monomers. So the question is, which one? And the hint is to figure out where the heck is this carbon that bears that methyl group. All right, we're losing a couple people as we go. Let's try and get back up to 49. Oh, so close. All right. Who votes for C? No one votes for C. Who votes for D? Yep, D is looking pretty good because that's right next to the carbonyl. This methyl group is next to the other oxygen, and we need to make sure that there are 2 carbons between the methyl group and the oxygen, so we're good to go. And so D is the right answer for that. So ring opening polymerization is not super special, but there are some details that we really need to sort out in terms of not gaining or losing any atoms or functional groups. We need to figure out what the mechanisms, cationic or anionic, look like. We're not going to study radical ring opening polymerization or ring opening metathesis, where we have olefins and other advanced polymerizations. You'll study those in your future polymer courses, but you should have an appreciation for the chemistry shown on this slide, and then maybe know a little bit something about silicones because they're really important, or polysiloxanes. Any questions or comments? Okay, so we tack that on at the end because I didn't want to overload exam number 2. And so we're going to keep moving, and you'll be able to practice ring opening polymerizations on the homework. The major topic in this section, along with what we're going to cover after spring break, is copolymers. And like we did before, we're going to study some chemistry of making copolymers, what they are, how to put them together. Then we're going to study some mathematics in terms of how to describe them. And we have some characteristic equations that matter for making copolymers. And we're, in general, going to focus on things like this. Statistical copolymers, and we'll talk about what that means. We'll talk about random copolymers, which are not the same. We'll talk about alternating copolymers, and we won't talk that much about block copolymers or how to make them in detail, but we'll cover some forms of blockiness. Where you cluster like monomers together, and we're not going to talk too much about graph copolymers. You just need to know that they're there. Key to this is that the different color dots, if you can see those, if you can't see the difference between these colors, just let me know. I'll make you a color neutral slide. But anyway, the different colors represent different monomer chemistries. So when we make a copolymer, in general, we'll have styrene and methyl methacrylate repeat units, or we'll have acrylonitrile repeat units, styrene repeat units, and some other type of repeat unit, acrylamide or something like that. And so when we studied step growth polymers, pretty much we could turn those alternating copolymers, right? Because we have RA2, RB2, RA2, RB2, and we would just alternate monomers. We didn't necessarily call them alternating copolymers then, but we're going to talk a lot about chain growth polymers and how to make copolymers out of them. And so this will make sense as we start to build up this picture. Okay, so copolymers, we have two different monomer types. And if we don't have a step growth polymerization, if we have a chain growth polymerization, the orange colored monomers can react with blue colored monomers. Blue colored monomers can react with orange colored monomers. Blue colored monomers can react with blue colored monomers. And orange colored monomers can react with orange colored monomers. And so if you look at this idea where the orange colored monomers incorporate faster in the chain than blue colored monomers, you're going to have more orange at the start. And then at the end, as you run out of orange, you're going to have more blue. That's really interesting. And this is also complicated because now we have 4 different types of reactions that we have to worry about if we're going to figure out which monomer is connecting to which. And so that type of chemistry and how to describe that chemistry is what we're going to be working on today and for the next couple lectures. So mostly we're talking about chain growth. We can have step growth copolymers, and we're just going to leave that aside for now. These are described using different methods. So what happens in chain growth polymers is that you know that the molecular weight increases very quickly as a function of monomer conversion, which means that you're making polymers making high molecular weight polymers across wide range of conversion. So in chain growth polymers, of course, you're making high molecular weight polymers here, 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 here. In step growth, remember, we had to go to high conversion or high extensive reaction in order to get high molecular weight. And that's the same for living, right? Living polymerization has a straight line. And so you need to go to higher conversion in order to get higher molecular weight in living polymerization. But we're going to be talking about the situation where right away, when you have this mixture of polymers or this mixture of monomers, what types of polymers do you make depending on the concentration of these monomers? So polymer composition depends on monomer concentrations. And you can think about that. If you have less orange colored monomers, you're going to have less orange colored monomers in the polymer, right? Or you're going to run out of orange colored monomers sooner, and then you only have blue colored monomers put in the chain. If you have no orange colored monomers, you're going to make all homopolymer blue, vice versa. So we can adjust the composition of this chain growth polymer by adjusting the relative compositions or the relative concentrations of the monomers. And that's what we're going to be building up the picture for. Any questions on this picture? Does anyone not know what this picture means? Okay, we'll continue to build up the chemistry picture for what this looks like. Okay, so if we have this polymer chain, and I'm going to switch from orange colored monomers and blue colored monomers to A monomers and B monomers. And so you have two monomers, A and B. And so if you have a growing chain, so this is a growing chain. And if you're making polymers that contain A and B monomers, it turns out that the active center could be sitting on the A monomer, if the A monomer is the last thing in the chain, or it could be sitting on the B monomer, if the B monomer is the last thing in the chain. And you can think about something like styrene plus methyl methacrylate. As you're building up this copolymer that contains both of those functional units, if in the process of growing this chain, because right, the active center moves from orange, orange, orange. Now the active center is blue, then it adds an orange. Active center is orange, adds another orange. Then the active center is orange, it adds a blue, et cetera, et cetera, et cetera. The active center is changing depending on how you're building up this copolymer and what monomer goes into the chain. And so you can have these two different active centers, and since they have different chemistries, they'll have different reactivities. Additionally, we have A monomer out here. We've got B monomer out here. When these active centers go and attack another monomer, those monomers have different reactivities. So we have two different active centers. We've got two different monomers. 2 squared is 4. So we've got 4 different types of reactions that we need to think about in order to build up this copolymer. If this is a confusing slide, it's worthwhile looking at this and thinking about this. But we have our A active centers, and we have our B active centers. And if the active center adds a monomer like itself, A adds A or B adds B, you get 2 like monomers together, and that's called homopropagation. Or the active center is reacting with the same type of monomer that it just came from. And now we have our 2 active centers again. Here's A active center, but it reacts with monomer B. B active center reacts with monomer A. And that's called cross propagation or heteropropagation. It adds a different chemistry than it is. So like I said, this is confusing, but now you see these little units that we build up. A reacting with A, B reacting with B, or the change in monomer chemistry. And you can see exactly on this slide where that might come from, right? Orange monomer reacting with orange, reacting with orange. That's all homopropagation. Up, orange reacted with the blue. That's a hetero. Up, blue reacted with an orange. That's another hetero. Homopropagation, et cetera, et cetera. And so now you build up a picture of what reactions have happened in order to get what types of linkage in the polymer. And we're going to describe that mathematically. We're going to talk about that. We're going to learn all about this on spring break, or we're going to learn all about this before spring break. And then think about it during spring break. All right, I'll see you on Wednesday. Don't forget your PLA.